So today you will be explaining the JVM memory structure, right?
Yeah, let's get inside. It's cold out here. JVM memory is divided into multiple parts. 1. Heap memory. 2. Non-heap memory, and 3. Other. Today we will focus mostly on the heap internals. Heap memory is the runtime data area from which the memory for all Java class instances and arrays is allocated. The heap is created when the JVM starts up and may increase or decrease in size while the application runs. JVM heap memory is physically divided into 2 parts, nursery or young generation and old generation.
Could you show us that pictorially?
This is how it would look like. We will not focus on the perm generation for the time being. Just keep in mind that from Java 8 perm generation has been replaced by metaspace. Don't worry, we'll cover the topic in my next class. Now let us get started with the heap internals. As I just told, that heap memory can be divided into young generation and old generation. Young generation is the place where all the new objects are created. When young generation is filled, garbage collection is performed. This garbage collection is called minor GC. Notice that the young generation is divided into 3 parts. Eaten memory and 2 survivor memory spaces is shown in this picture. Now we need to keep these in mind when talking about young generation. Almost all of the newly created objects are located in the hidden memory space. When hidden space is filled with objects, minor GC or scavenge GC is performed and all the survivor objects are moved to one of the survivor spaces. Minor GC also checks the survivor objects and move them to the other survivor space. So at a time, one of the survivor space is always empty. At the end of the scavenge GC, the Eden is empty, since all the reference objects are now in the survivor space and ready for object allocation. Objects that survived after many cycles of GC are moved to the old generation memory space. Usually it's done by setting a threshold for the age of the young generation objects before they become eligible to promote to old generation. Now we also need to understand that the scavenge GC's efficiency depends on the amount of reference objects it has to move to the survivor space, and not on the size of the heap. The higher the amount of reference objects, the slower the scavenge GC. Studies have, however, shown that most Java objects live for a short time. Since most objects live for a short time, one can typically create large events. Reference objects in the survivor space bounce between the 2 survivor spaces at each scavenge GC, and this bounces until it either becomes unreferenced or the number of bounces have reached the tenuring threshold. And if the tenuring threshold is reached, that object is migrated up to the old heap.
So you mean that objects that have survived after many cycles of GC are moved to the old generation memory space.
Exactly. Usually it's done by setting a threshold for the age of the young generation objects before they become eligible to promote to old generation. When the old generation becomes full, garbage is collected there, and the process is called as old collection. Now I told you that old generation memory contains the objects that are long-lived and survived after many rounds of minor GC. Usually, garbage collection is performed in old generation memory when it's full. Old generation garbage collection is called as major GC and usually takes longer time. When that is done, the JVM sweeps the entire heap to reclaim all free memory, for example, because the object is now dead. Now, by this time you must have guessed that the reasoning behind a nursery is that most objects are temporary and short-lived. The young collection is designed to be swift at finding newly allocated objects that are still alive and moving them away from the nursery. Typically, a young collection frees a given amount of memory much faster than an old collection. So much for today. I will continue perm generation and metaspace and other memory in my next class. Don't want to bore you off to sleep.
This was an interesting class. See you in the next class.